Hey everybody, this is a little video that's going to help you with the groundwater lab. It's going to cover contour lines and flow lines. So we're going to talk about both of those here in this first section. Contour lines are just lines of equal elevation. So on a surface like the land surface, here we have two little hills, and they have drawn on these contour lines, which are just lines that show what the elevations are at different levels here. So right here, every spot on this line, this dashed line, is 250 feet. Every spot on this line right here, this dashed line, is 200 feet of elevation. And it goes all the way down to sea level, which is 0 down here. Okay? Contour lines can never cross, and they can never intersect, right? It'd be impossible to have a 250-foot contour line and a 200-foot contour line in the same place. So they never merge, they never split. They're just lines of equal elevation. And the point of drawing contour maps is to be able to show you what the topography looks like. Now, flow lines show us what direction water would flow over a surface, okay? So on a hill like this one, if I draw a little point source here, the water is going to flow straight down slope like this, right? The water is never going to flow sideways down a slope like this. That's just not going to be possible. It would kind of go against the law of gravity there. So it's only going to cross contour lines at a 90-degree angle. So every time a flow line crosses a contour line, it's going to be perpendicular like this. So this intersection point right here is always going to be 90 degrees. And that is just because water can't flow sideways down a slope. Another kind of interesting thing about contour lines is you can tell what the elevation is at any point on the map. For example, right here, if I was going to try to figure out what that elevation is, what do you think? Well, I'm going to assume that there's a constant slope between the 200-foot contour line and the 150-foot contour line. And since this is about halfway in between those two lines, I'm going to say that this elevation is probably about 175 feet. Okay? All right, so water is always going to flow down slope, and we can find out what the elevation is between contour lines just by kind of extrapolating in between, okay, and estimating. It looks like, for example, they were saying that the very peak of this mountain right here is about 270 or 287 feet high. Notice that it's just under this 300-foot contour line right here. Okay, so that's going to represent that elevation. Over here, the peak of this little hill is just under 200 feet. So they're saying that it's 193 feet right there at the very peak of that one. And this would probably be just about right there, just over the 100-foot line. That would be the elevation of that spot right there. Okay, so we've got two hills, a big hill and a small hill. Over here it looks like there's some kind of a drainage, so there's probably a stream that kind of drains off to the right here. Okay, so big hill, little hill. Now we really don't need contour lines in this diagram to help us figure out what we're looking at. We're looking at two hills, a big hill and a small hill over here with kind of a little saddle in between. If we scroll down a little bit, we'll see what contour lines would look like in a two-dimensional drawing. Okay, so these are the same contour lines, but we're kind of looking down on these two hills from above. Notice that here is that little drainage, so water is going to be kind of draining off that way. And notice how the contour lines form little V's that point upslope. Okay, so the water is flowing down this way, the contour lines V in the upstream direction. So back to our contour lines. So again, I put a little dot right here last time, and I drew a flow line that was perpendicular to these contour lines, and it kind of went something like this. Now I don't really have a protractor or anything, but I know that this is approximately how water would flow over this surface. How would it flow over here? Well, I'm going to use the same principles, and I'm going to just draw the flow line perpendicular to the contour lines, which are black, and it's going to go just about like that. And that makes sense, right? Here's the peak of the hill. Water's going to kind of drain off in all directions away from the peak and perpendicular to the contour lines like that. Same thing over here. If I were to draw flow lines from this spot right here, they would kind of look like that. And over here, the flow lines would look like that. So once we have a contour map, we can figure out which way water is going to flow over that surface, no matter where we're at. Okay? All right, so let's take it to the next level. So these represent hills. On this picture right here, we're looking at a contour map of the water table. So what they did here is they drew contour lines, which are labeled right here, and they drew a contour map showing the elevation of the water table. So this map represents sort of the subsurface, the water table underneath the ground. Now the ground probably slopes in the same sort of direction and has the same topography as the water table, but we don't know that for sure. So they actually used well data to compose this map right here. And then what they did is they drew flow lines right here in sort of a dashed blue color that show the direction that the water is going to flow over that contour map. Okay, so again, the contour lines are in black here, and their flow lines are in blue. Notice how they drew them perpendicular to the contour lines. And notice that they eventually go into this blue gaining stream. And just like the previous map, the contour lines point in the upslope direction. So I know that this stream is flowing kind of down towards the lower right. Well, if this is north, the stream would be flowing down to the southeast, okay, going down in this direction. Arrow there. All right, so we can tell which way water is going to flow anywhere in this map. Everywhere we see contour lines, all we have to do is draw a line perpendicular to those contour lines, and we know that that's going to show the true direction of water flow along the water table here in this picture. So let's take a look at this area over here where they have a well. So if we have contour lines and we draw some flow lines, we can tell whether or not a well is in danger of being contaminated. So what they're showing here is a well without any cone of depression, and that is represented by the black contour lines. And then they show what would happen if they started to pump heavily out of this well and they created a cone of depression, and that changes the contour lines and makes them into this shape here shown with the red. Okay, So let's look at what would happen if we had a contamination source right here. So this is going to be a contamination source, maybe a dump. Contamination. The mouse is slow. Okay. So the question is, without the cone of depression, would a contamination source right here go into this well and contaminate it? And the answer is, well, let's find out. Let's draw a flow line from this contamination source. Under the present conditions, in other words, the black contour lines, the contamination source is going to cross them at 90-degree angles, and look at this. It's going to miss the well and go into the gaining stream down here. So everything is good to go. As long as there's not a cone of depression, this well is safe. In fact, if we had another contamination source right here, put another arrow there, it's also going to miss, right? Because we could just follow this dashed blue line, and if we draw 90-degree intersections, it's going to go right past the well and miss it. So the well is safe under these conditions, okay? But look at what happens when we start to pump water out of this well and we create a cone of depression. Everything changes. So I'm going to go here and I'm going to pick a green color and draw what's going to happen with this well, pumping water and making a cone of depression. So from the same location, look what happens if I draw 90-degree contour intersections. It's going to kind of curve like this, and in order to hit this guy, I have to hit it at 90 degrees. That's going to be like that. So notice how it's curving right into the well. And a contamination source over here is going to do the same thing. It's going to come right down. Everything's the same until we start to encounter the cone of depression, and it starts to turn. And again, right here, I have to intersect at 90 degrees, right? Because water is only going to flow down slope, and it's going to draw that contaminated water right into the well here. So under these conditions, with the red contour lines and the cone of depression, anything in this entire region right here is going to be swooped right into the well. All of this water is going to now flow into the well. So if there are any contaminants in this area, these guys are going to be in bad shape and their well is going to be contaminated. Okay? They're still okay if there's a contamination source out here, right? So this is still, even with the cone of depression, I'm going to draw 90-degree intersections. It's going to come closer, but it's still not going to go in, and it's going to kind of flow down that way. Same thing if I had a contamination source over here, it's going to miss the well. Okay? So there's a danger to creating a cone of depression, right? The bigger the cone of depression, the more you're going to funnel potential contaminants into that well. So in this case, the well would be in bad shape. So let's look at what this gaining stream right here does. Okay, so I've got a gaining stream going this way, and let's just say I have a well on the downslope side of this. So here is my well. And over on this side, I have a toxic waste dump right here. In fact, they buried radioactive waste right here on the other side of the stream. The question is my well going to be in danger of contamination from this source right here? You might think, oh man, this is bad bad news, right? This is going to potentially contaminate the well. But let's look at what's going to happen with respect to the gaining stream. Now, for the record, I definitely wouldn't want a toxic waste dump right here if this was my well. But we're probably going to be okay. Because look at what's going to happen if I draw flow lines. From this side of the toxic waste dump, it's going to go right in here to the gaining stream, like that. And over here, it's going to go parallel to this flow line, and it's going to go into the stream over here. So this whole zone right here will be contaminated with whatever's in that toxic waste dump. Inside the lines there. Get rid of that. Oops. Let's redo this. So all of this stuff in here is going to be potentially bad news. Will it come up and out of the other side of the gaining stream? Will it come over here and get into the well? The answer is no. So what's going to happen is all of this toxic waste goes down here into the stream, and once it's in the stream, it becomes a surface water contaminant and just goes right down the waterway here. What it doesn't do is come up the other side. So this well is actually going to be safe under these conditions. Okay? So let's take a look at why. Why doesn't it come up the other side? Why is this well safe? Well, let's look at a cross section of this stream right through here. So if we look at this picture, let's just say that this is the side with the contamination source. What's going to happen is this is going to flow into the gaining stream like this. And then once it's in the stream, it's just going to come straight down this way. What it can't do is come up and defy the law of gravity and come up and contaminate a well on this side. So this well over here would be safe. Is that making sense? So contaminating or a flowing stream like this, or a gaining stream, is going to provide a natural barrier for groundwater contamination. Nothing on this side can get over here and contaminate anything on this side. Okay, so any contaminants that are on this side of the map area are going to stay on this side of the map area and just go into the stream and flow down the stream. And this side will be in good shape. Okay? All right, so we got that down, got the flow direction figured out, what will happen and why contaminants can't go up onto the other side here. Let's take a look at what we'll do on the lab. So here is kind of the first diagram that we'll have to draw on. So here is a point for flow lines, and it's just asking you to draw flow lines for the water table in this diagram. Let's just start at the bottom here, and we're just going to follow the 90-degree rule again. So if I was to draw a flow line from this little X right here, all I'm going to do is eyeball this and go, well, it looks like it's going that way. Right off the map area, this is going to be a 90-degree angle right here. Okay? I do the same thing from this one, and I just kind of eyeball this and go, well, it looks like it's going to go this direction. Okay, so my green flow line is going to intersect these contour lines at 90 degrees perpendicular. And from here, I'm going to kind of do the same thing. I'm just going to eyeball this. That looks like 90, 90, 90, and then it's going to go into the gaining stream here. And once it's in the gaining stream, it's just going to go straight down that way. Okay. What it's not going to do is not going to flow up onto this other side here. Okay, so now we have some flow lines, we can get an idea of where these different contaminants are going to go. So I'll do a different color here. Let me get back to some orange again. And I'm going to just kind of show you what's going to happen with this dump site. So to draw the contamination flow pattern here, I'm just going to kind of pick the edges, and I'm just going to draw lines that go parallel to my flow lines. Not doing the best job, it's a little wavy there. But this whole zone right here is going to represent a potential contamination zone from this dump site. Okay, it's going to go all the way out here. Okay, so this whole orange zone right here is going to be bad news. The groundwater is going to be contaminated potentially in this area. Okay, so let's draw the contamination zone from the septic field. I'm going to do the same thing. I'm just going to kind of draw a flow line from this side, and it's just going to go like that right into the gaining stream, and on this side it's going to do the same thing. It's going to go kind of parallel, and this is what that contamination zone is going to look like. Okay, so under these conditions, both the dump site and the septic drain field are going to move away from these two wells. These two wells are basically safe under these conditions. The dump site is missing, and so is the septic drain field. Now, one of the questions that it's going to ask a little bit later is, what are the elevations of these two wells before and after pumping? Here's a contour line that says 108 feet, and this contour line is 112 right here. So 112, 108. What would the elevation of well 2 be? Well, it's kind of roughly halfway between the 108 and the 112, maybe about 110 feet. In well 1, looks like it's a little closer to the 112 line. So it looks like its elevation might be around 111 feet. Right, so this would be 108, maybe 109, 110, 111, and then 112 right here. Okay, just kind of equally spaced there. So 111 feet for this well, 110 feet. And again, we're looking at the elevation of the water table, not the land surface here. Okay. All right, so everything is sort of hunky-dory in this scenario. Everything is missing. All the contamination is missing these two wells. Now remember, well 1 is actually their drinking water well, and well 2 is the Jackson's agricultural well. So this is what they're using to water crops with. So they develop this well, and they start to draw down the water table around it. In this diagram, they kind of show what that looks like. Notice the huge cone of depression here. So even though this is their drinking water well, it still went down a little bit, right? I think we decided that it was about 111 feet. Well, this is the 108-foot contour line, and this contour line right here is 104. So now this well has dropped down to maybe 105. And look how far well 2 has dropped. This looks like a 72 down here. So it's way down from what it used to be. So let's look at how that affected this toxic waste dump over here and the septic drain field. Again, I'm going to draw lines or flow lines perpendicular to the contour lines, and look what's going to happen. It's just going to go straight into well number 2. Right? It's no longer going off the map area like it was in the previous diagram. It's all going into well 2. Also, look at what's going on with the septic drain field. Some of this waste could potentially go right past well number 1, which again is their drinking water well, and contaminate it. But notice, none of this stuff right here is going into their drinking water well. It's all just being sucked right into well number 2, which is their agricultural well. Okay? So this is kind of the point of all this, being able to draw flow lines and figure out what's causing certain wells to become contaminated. All right, let's move on and let's look at some side views. This is from the reading, and this is a model that just kind of shows you what artesian wells look like. So this aquifer that's sandwiched in between these two aquicludes is our pressurized artesian aquifer right here. Okay? So this is the pressure surface, and this represents how high water in this confined aquifer right here would actually rise if it was allowed to. So here they dropped a well into the aquifer at this location, and notice that the pressure surface right here is above the top of the well. So water sprays out onto the surface. So this well specifically would be a flowing artesian well. Over here, notice that the pressure surface is below the top of the well here. So here's that pressure surface. Water does indeed come up, but not all the way out onto the surface. So this is considered a non-flowing artesian well. Okay? What kind of a well would form if I happened to drill it right into the top right here? Well, here the water would only go up to the water table. It's not pressurized at this location. So if I drew dropped a well right here, it would just be a water table well. Okay? So this is what this side view is looking kind of explaining. Let's go down a little bit here and take a look at this diagram, which is in the lab. So let's look at what we're up against here. This is representing the pressure surface. I'll put PS for pressure surface. And this is just the land surface. Okay, so this sort of mimics what was in the last diagram. We've got a little hill right here, and we've got these sloped or dipping rock layers here. And if we look at the key, this is shale here and here. Okay, so this represents the aquiclude, and this is water saturated sandstone here and here. So these are our two aquifers, one up here, one down here. Okay? So this aquifer is the one that's pressurized. This is the one that's going to produce potentially artesian wells because it's stuck in between these two aquicludes here. So let's kind of look at how far water in these different systems is going to flow. Here's this is a non-flowing artesian, and it's just going to go right up here to that line, and D is the same. It's going to kind of go up to this line. And G is a flowing artesian well, so it's actually going to go up here and flow out onto the surface because the pressure surface is above the land surface at this location. C, looks like they didn't quite make it into the aquifer here, so in this case, it's just a dry well. If they spent a little more money and were able to drill down into this aquifer, it would be an amazing well. It would be a flowing artesian well, and water would flow all the way up to the pressure surface here. Here is a toxic waste dump. So the question is, which wells are in danger from this toxic waste dump? You might think, oh, D and G here are in bad shape because this is right above them and it's just going to go down and get in there. But it's not, because this shale layer is going to act as an impermeable boundary, And so instead of soaking in, it's just going to kind of go into this aquifer right here. It is going to trash E and F, but it's not going to be able to sink down in through this impermeable layer and contaminate D and G. They will stay clean. Okay? All right, so that's what's going on with this side view diagram here. Again, this is the pressure surface up here. It's kind of a more generic diagram of what we saw up here in this one. Okay, but a little more complicated because we have an extra aquifer up here, only this one's not pressurized. Okay. All right, so it looks like we've got everything covered here. Hopefully this is going to help you out with the lab. If you have any questions, obviously check in with me and just ask if you do have questions. All right, good luck.